in this mini course that was organized thanks to Stefano and Matteo here. So let me introduce a little bit the idea. We were contacted by Stefano and Matteo. They were visiting Brazil and other institutions, and they asked, let's say, they were looking for possibilities to present this mini course on quantum computing, and we were very happy about that. And the mini course, as far as I understand, will be very practical. Like after a brief introduction about the theory of quantum computing, they will immediately move towards exercise, coding, and so on. So it will be hopefully very funny for all of you. And they are building, I would say, the main driving force behind this Qibo, this library about quantum computing. So will be an opportunity to learn quantum computing and to learn the basics of this library that they are developing right now. So without further words from me, let me give the floor to Stefano, and he will start now.
Thank you so much. Thank you, Dario, for the presentation, the introduction. And yes, it's for us, for Matteo, for me, it's a great pleasure to be here. And well, also to see the organization, the great organization that we have to help perform it. And today we are dividing the presentation into two blocks. So we start with a short introduction about quantum computing, and then we move on to more specific topics that are usually quite challenging and interesting in quantum computation. So let's have a look at these slides. I like usually to talk about the introduction. Huh? Yes, it works. Yeah, so usually what I like to do when I start talking about quantum computing is to show this plot. So in this plot you see a very simplified timeline in years from the beginning of the century and some key points in classical computing, like in 1930 the Church and Turing experiments papers, 46 ENIAC, in 50s the Shannon entropy definition, and then we have other challenges and other points which have been interesting in that area. But then in 2010 we have the born of deep learning, machine learning. So nowadays we are really surrounded by applications that are involving classic computing, graphics card, multi-threading CPU. So we are really very technological at this stage. Now if you compare this timeline, the classical timeline, to the quantum timeline, you see that quantum mechanics was born at the beginning of the century, and then we have in 26 the postulates, 47 transistors, in the 60 lasers, and then many others like GPS, the factorization theorem, the World Wide Web, which was a side product of having quantum computing. If you remember, the WWW protocol was developed at CERN in Geneva, and in order to transfer data collected at experiments, colliding particles. No? And this is, again, a side effect of quantum. And similarly to the classical world, in 2005, so around the same ages, we have the definition of the first quantum gates, and then in 19, one of the first papers about quantum advantage. So there is a threshold in both diagrams that is around 2000, where we have advanced AI from one side with deep learning models, and at the same time we have a huge progress in quantum computation with quantum information. And nowadays the question is, how can we use or even combine both worlds and have something useful for our applications? So what is happening? So if you look at this plot, you see that many of our codes nowadays, they are written still on CPU, so the computing process unit. And those devices are general purpose, so we can do whatever you have in mind. You can write an algorithm, solve an integral, or even write a web page and do any classical computation. So we are surrounded by this technology. Now, physics is also transitioning and trying to use graphics process units as much as possible. For example, for Monte Carlo event simulation or linear algebra in general. But what is very, very complicated here is that we have to spend a lot of time translating our code to a target like a GPU. So you have to learn CUDA, you have to learn OpenCL, ROCm. So the luggage in terms of experience that we have to carry on is extremely different from that. Now, moving to more recent technologies, we have the field programmable gate arrays, which are very specific chips where you can design your algorithm directly on chip. And those devices are extremely powerful because you can design and write explicitly the operations that you are planning to do. The advantage of doing that is that you get a massive improvement in performance. You can get results very, very fast. The power consumption is also very low, so this is extremely useful. However, the complexity and the flexibility to do computations is still very, very high. So for example, if you have computations using double precision, FPGAs today are not really so easy to use. And then I have put it here on the right side, the quantum chip. So this is the most challenging, still a research and development device. But the idea is that we are transitioning from a general purpose system to an unconventional system, a system that is designed for a subset of applications. So something that is very, very specific. I am not planning to do the same computation that I usually do on CPU. I'm trying to just identify those operations that are extremely efficient on the quantum chip. So this is the landscape that we have nowadays. Now, quantum technologies, they have been distributed and they have been discussed in many opportunities. There are many international grants that are funding research on that topic. And usually we like to show quantum computing and other quantum technologies in this diagram. So you have the basic sciences and then quantum communication. So how to transfer quantum states from one place to another. For example, teleportation, quantum key distribution algorithm. Then we have quantum computing, which is the topic that we will talk today. So how to use quantum systems to perform mathematical operations, execute algorithms. Then we have simulation, which is extremely important because unfortunately, at the moment, we don't have perfect quantum chips, quantum systems. So we have to deal with experiments. Those experiments are noisy, so we need simulation. We have to understand what we have to do in order to obtain a good result or interesting algorithm to try. And finally, the last pillar is quantum sensing or metrology. So it's the science where we try to use the chip to detect and collect information from nature. And this is one of the most interesting parts of all this discussion, because if you are able to use quantum to connect with data, perform, like for example, design a detector, you could have a quantum data representation in the Hilbert space, and then you could send this information to any other quantum computing system. No? And that's the most, say, exciting part of all this discussion. So all these four pillars together is usually the definition of quantum technology, and is the paradigm that we are trying to exploit. When I show you the timeline in the second row, no, in 2019, I was saying that there was this quantum advantage, quantum supremacy. So in fact, what I was referring to was this paper from Google in Nature in 2019, where they managed to create a grid of qubits, the one that is represented here, where we have the qubits represented by these gray crosses and adjustable couplers in blue, creating a system with 53 qubits, with in total 86 qubits couplers. And they managed to demonstrate, at least at that time, that computation, some specific computation using this chip was possible, while with the equivalent using classical simulation was not. So that was the claim at that time. Obviously, there are many discussions about if this is really a quantum advantage or not. However, in the paper, if you have a look, you see that there is a clear benchmark in these terms, in terms of years that we would require in the classical system to achieve the same amount of computations that they manage with 53. That happens because quantum states are much larger than classical states, so you need a lot of computational resources to simulate. Now, before jumping into more physics, this is just an introduction. Here I'm showing the effort in 2015 in terms of funding that quantum technology has received in Europe and other countries. And as you can see, we are reaching, at that time, the world was reaching something like 1.5 million and spread it among all the different continents. No? So you see that the effort was extremely large at that time. And if I go further, and if you look at even more recently, for example, the last years, you can see that there are several companies that are also interested in quantum technologies. This is something very specific to quantum, because in the past we never saw a situation like that, where companies, IT companies, AI companies, they have put a lot of money on that. And if you look at the volume of funding for spin-off startups, you can see that there is an exponential growth since 2000. So in 2021, we reached 1.7 billion in investments for companies looking into those technologies. When we talk about quantum technologies, we mean the company that manufactures a qubit, or the company that will generate or build an instrument to control the system, or the company that is designing the superconducting environment that is needed in order to operate the quantum chip. So as you can see, there is a lot of people looking into those topics from academia since the beginning of quantum mechanics, but also in companies. So the world is really interested on this synergy between academics and industry. Now let's jump back to quantum systems, and let me try to explain why we need simulation and why we are talking about Qibo. So what is Qibo at the end? Why we are doing this now? So let's think that we, for example, consider a grid of particles. So here we have n particles distributed in a grid. If you wanted to represent this system with n particles, this can be quite complicated, because we might have problems such as, for example, if you think a system based on a two-state, spin up, spin down, we have to deal with a 2 to the n dimensional space. No? And these spaces can be extremely large, because if you just take 30 particles, you are already representing a state which is composed by 2 to the 30 objects. The numerical representation usually is complex numbers in double precision. So you are just filling the memory of your computer with more than 16 gigabytes of RAM. No? So if I now think about a system with hundreds of qubits, well, I am really far away from 6 terabytes of RAM. So my computation becomes quite complicated in a classical computer. So I have a very challenging time in building a system that can operate and execute my algorithms. Now, what can we do? Well, we can try to, as I write here, we can try to use the classical methods to represent the system, which is the basis of simulation. We can then eventually build our experiment, so try to implement qubits directly in practice. This is what, for example, we have seen so far with Feynman's and all the people involved in quantum, the possibility to design special systems where we can attach the qubits downstairs in a cryo and then control the chip. But obviously, as we said, and as Feynman said, nature isn't classical, damn it. And if you want to make a simulation of nature, you would be better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. At the end, we are there. So we are really trying to understand what is the best approach to represent the system. So talking about quantum computing then is the basics in order to build our system. So the first ingredient consists in defining a qubit. So a qubit can be implemented from a mathematical point of view. Is a classical bit represented by a state, psi, for example, as a linear combination of two states, the ground state and the excited state. If I do that, then you already see the power of quantum computing, because a qubit is not a binary system where you have only 0 or 1. It's a continuous state, so I can have an infinite amount of states. I have just to tune the two coefficients alpha and beta, and then I have the full representation of my Hilbert space for this system. Qubits can be implemented in practice using multiple technologies. For example, superconducting loops. We take cavities. We put these cavities at very low temperature, and we send photons. These photons will oscillate inside the cavity and create the behavior of an harmonic oscillator. and we can tune the current in order to create states. So you can have a state at a ground state or excited state. So this is the cheapest technology that we have nowadays. So it's very easy to design and fabricate.
The transmods are this one.
Yes, the transmods are this one. Exactly. And this is exactly what as Dario was saying, is the most popular. If you go to IBM, if you go to Rigetti, if you have a look at the companies that are implementing, they are fabricating a massive amount of transmods based on these technologies. Also us, for example, I'm from Italy, and in our university, in our framework, we are also building, because at the end of the day, the involved costs are very low. But there are many caveats, and we will discuss about that later. Now, there are more fancy and interesting architectures like trapped ions, where we have ions and we can manipulate the ion states. And this allows us to really increase the amount of qubits and the amount of possible interactions that are available. And then we have more exotic systems like silicon quantum dots, topological qubits, and so on and so forth. Today, we have 90% of the available systems based on superconducting loops, and just a small fraction that is looking for trapped ions. Now, there are companies like IonQ, or there are even universities designing proper optical systems that can control pretty well this system. Yeah. So the second point, supposing that we know how to design qubits, is how can we manipulate, how can we apply operations to the qubits? No? Because obviously I can represent my state, but then if I cannot control the state, I cannot do any computation. So what we do here is that we define quantum operators. Now, the usual way we do quantum mechanics. So if you have your initial state psi, we can define an operator, eventually a parametric operator like I'm doing here, and this operator will modify the psi state into a psi prime state. So, and this is exactly the manipulation, the basics operations that we want to do. So the question is, how can I define an adequate and a clever set of gates to solve my problem? And these gates can be for a single qubit, but also can be applied to multi-qubits at the same time. The third point is how to combine everything that I said before, states, gates, qubit technology, into an algorithm. And this can be done through the quantum circuit representation. So here you have this design, that is is the translation of the mathematical representation that we can design by hand. For each qubit, we design a horizontal line. We put at the beginning of this line the state. So here I have the ground state, the zero state, so the ground, not the excited state. And then moving to the right, I apply gates. For example, this is a rotation, this is a control knot, and I go up to the end where I can perform a measure of my system. So I'll explain you all the details, but just to give you an idea, what we're trying to do. We define a system at a specific initial state solution, so the psi in this case will be the ground, and then we apply operators, and those operators will change the state, and when I collect the measure at the end, I have the final state. So my psi prime will be reflected by what I collect here at the end. Finally, as I mentioned also in the previous diagram, another challenge when dealing with quantum computing is that, yes, we can have a system at the initial state and then apply an operator, but we have to measure. So we are dealing with an experiment at the end. So measurements, they can be noisy. We have to define how many observations we want to do, what is exactly the observable that we are planning to measure. So, and this is a challenge, also a challenge when trying to design a proper algorithm. Okay? So those are the 4 points, the basic points that we have to really understand and try to implement in order to do quantum computing. Now, what is a qubit, as I said? In the previous slide, I just mentioned briefly that you could represent the qubit in the Hilbert space. And what we do is that we define a two-dimensional Hilbert space with this the computational basis composed by the ground, 0, the ket 0, which is represented by, in linear algebra, by the vector 1, 0, and the state 1, the excited state, that is represented by the state 0, 1. So these are the two bases. And then a quantum bit will be a linear combination of 0 and 1, where alpha and beta are coefficients, complex numbers, with normalization equal to 1. So if you put the square of and sum up, you should get always 1. So this is the finish. And as I mentioned before, this state is continuous. So this is something extremely different from classical computing. Now, if I take more than one qubit, so if I combine, I try to create a system with 10 objects, 20 objects, well, what I can generalize this representation and say that a system with n qubits will be a 2 to the n dimensional Hilbert space. So you can create all the compositions. The bases that will represent those states are the ones that you see here. So I have the 0 n with all the qubits at 0, the 1 state with just the last one at the excited one, and then I go up to the last state where all the qubits are at the excited state. So I generated this huge base, but the idea is always the same. Oh, I can write my final state as a linear combination of all these ingredients, all these elements from the basis, multiplied by coefficients, complex numbers. Also in this case, the coefficients are normalized, so I have to make sure that everything is consistent when represented. So I have a really very simple way to generalize. When I apply to the state a unitary gate, for example, here I get my initial psi, and I apply the U1 and then the U2 operators. This will generate the psi prime state, and this operation can be translated in the diagram that you see here on the right, where I start from psi, then I apply the U1 gate, then the U2, and I get the U psi prime. So this is the typical example of operation. From the mathematical perspective, if you wanted to compute numerically the psi prime, we have to perform this tensor dot operation, where we do the contraction between the matrices U1 and U2 to the initial state psi by running over the target gates. So in principle, it's very simple to do that. So you can implement this algorithm in any computer. It's just a tensor dot, it's a matrix vector multiplication. The problem is the size. So the size of psi, if you remember, is 2 to the n. So if n is large, I don't have memory. So unfortunately, I cannot go beyond a threshold. No? So this equation that you see here, the exact cat approach to quantum simulation will be bound by memory. Now, talking about gates, there are some subset of gates that are more interesting than others. In particular, here in this plot, you can see those that are very famous and commonly used in our field. We have a single qubit gates, such as the Pauli matrices, the Hadamard, the phase shift, and the rotation gates. We have 2 qubit gates that are those that are connecting 2 or 2 qubits at least. You have a control and a target. And finally, you can also have 3 qubits, like for example the Toffoli gate, where you have connections, target and controllers from more than 2 qubits. Let me show you some examples. On the left, if we take the X gate is represented by the Pauli sigma X matrix, composed by 0, 1, 1, 0. So if you take this object and we multiply by the ground, what happens is that my state flips from the ground to the excited state. So the behavior of the X Pauli is exactly the same as we have for the classical NOT gate. No? When you apply it, you flip the state from 0 to 1. Similarly, if I start from the excited state and then I apply the X, I go back to the ground state. So this particular gate is the responsible of this flip. On the right, you can see the Z gate. So the Z gate is using the sigma Z Pauli matrix. And what he does is the following. If the state is at the ground, nothing happens. But if the state is at the excited state, if the initial state is at the excited state, then I see the minus sign in front of my state. So it flips the sign, only for the excited state. So those are typical examples for single qubit operations. Now, if I complicate the system, I can, for example, define the Hadamard operator. as you can see here, is this matrix 1, 1, 1, minus 1. And if I take the ground and I apply the Hadamard, this corresponds to generating a state that is a superposition between the 0 and 1. So in particular, this will become the plus ket state with the plus sign. If I do the same for the excited 1, I generate the superposition 0, minus 1. So again, this, for example, is a quite interesting state because we have already something that classically is hard or even impossible to do, generate states that are into two states at the same time. No? Yeah. Now, the Hadamard, if you try to measure, it will give you some results. For example, if I try to apply to the ground state Hadamard and then measure, what I should expect to see is this superposition, 0 plus 1, normalize it. And if I do the measure in my lab, what will happen is that you see 50%, I should see 50% probability of measuring 0 and another 50 of measuring 1. And that's the connection that I was trying to mention before. Measuring will make our representation harder because I have to make sure that the amount of data I have collected is sufficiently to represent my state in the proper basis. So if I do just 2-3 measurements on that system, I will not be able to see the 50-50% distribution. I have to increase that number of shots. And moreover, if my system is very noisy, I have to deal with statistical and systematic uncertainties. No? So all that is important, and we are facing all those issues nowadays when measuring and when designing algorithms. Okay, so now let me do this example again now, just to emphasize. If you suppose that we have a quantum chip, we define a state at the ground state 0, then we can prepare the superposition by applying, for example, Hadamard. So I do Hadamard at 0 is equal 1 square root of 2, 0 plus 1. So my psi ket, plus ket with the Hadamard operator and the 0 and 1 as I defined it in the previous slide. If I generate a control knot, so if I apply a control knot to this particular setup where I have my superposition from one side and the excited state and the second qubit at the ground state, what will happen is that the control knot will be applied only to the state with the control qubit at 1. And in particular, in this case, what happens is that the control knot will not do anything with the 0 qubit here multiplied by the second qubit 0. So this state will still there. And we shift only the operation to the 1, 0 state. So the knot is only applied to the second member of this equation. If you do that, if you do so, the knot operator will flip the second qubit state from 0 to 1. So you see that the knot has changed this quantity here into 1, 1. So now I have a state that is an entanglement. So this is an entanglement, something that is impossible to do with classical computing. The graphical representation of this operation is the one that you see here. I have 2 qubits. I apply the Hadamard to the first qubit. So after applying the Hadamard, I have a superposition state for the qubit 0, so the first one. And now, if I do the control knot, I can flip the state of the target qubit from 0 to 1. And then I measure, and I should get a superposition state. No? So this is the typical operation that we cannot do absolutely in any way classically. Another set of operations that are usually quite important now, if you look at our introduced state psi, you have the alpha plus beta. You can do the Bloch sphere representation by converting the alpha and beta coefficients into angles. So you can write alpha as the cosinus of theta over 2 and beta as the exponential times sinus theta over 2. So if you do that, then our state can be represented in a 3-dimensional Bloch sphere, so it's a sphere, and will become just a state vector. So for example, here you have this arrow pointing upstairs. When we apply an operator, the operator will move my initial state that is represented by this arrow into another place. For example, as in this case you see, there is a rotation and a projection, so I get a psi prime that is pointing to the minus y range. No? So these kind of operations, rotations over the Bloch sphere, can be represented by a special set of gates that are called the rotation gates, and that are composed by the exponential of minus I, theta, which is the angle, and sigma k, where sigma k is any matrix, any operator from the unitary to the Pauli matrix. So based on, if you follow and if you decide to use one of those rotations, then you get the effect of seeing your state rotating. And this is a parametric gate, which is interesting for us because you can fine-tune the angle in order to move the state to the position where you need it. No? If you have an algorithm that might want to project the state into the equatorial line of your system, that's the possibility. So if now we suppose that we wanted to represent this qubit system, for example, the spin up and down, and try to compute this quantity, what we can take in consideration is the following. I take a float 64 system, which was composed by 8 bits of memory for each qubit. Each representation of a qubit relies on the complex number representation with 2 float 64, so it's in total a complex 128 number, so 16 bytes of memory. So if I generate a system, for example, 32 gigabytes of memory RAM of our computing, I can store up to 2 billion complex 128, which seems a lot, but as you can see, if I just select 30 qubits, this 30 qubit state is already at 1 billion complex numbers. So you see that the system can really go beyond the common usual memories that we have available quite soon. With only 30 qubits, we are already at 1 billion complex numbers. A 31 state cannot be represented for sure in our computes here, because we are bounded by 60 gigabytes, so we cannot do any simulation on my laptop, or, well, if I need more than 32 gigabytes. The memory will scale a lot, so you can even go to larger infrastructures like Fugaku, which is a supercomputer, or any other infrastructure. But at the end of the time, you can see that even Fugaku, with all its memory, cannot go beyond 50 qubits. So that's a very important point. If you wanted to do exact simulation, the scaling is very bad. And I can do whatever I want. I can buy expensive machines. I can buy a lot of memory. But due to this infrastructure, the complex 128 representation, memory will explode quite soon. So there is no simple way. Now, fortunately for us, there are some smart techniques that can be put in place that usually are not based on exact simulation. And those are, for example, the ones based on the variation of Monte Carlo. So we define our wave function, and then we try to maximize the integral that you see here using Monte Carlo. This approach is usually acceptable. The problem is that we have uncertainties. So we have lots of uncertainties that are due to the variance of the Monte Carlo approach. Other approaches are based on using tensor networks. So you can represent our operator, our state operator, as a product of smaller states. So you can simplify huge systems into smaller pieces, and those smaller pieces can be split into multiple computers, multiple devices. So you can do it on GPU, CPU, multi-node CPU. And finally, we have even technologies like neural network quantum states that are using artificial neural networks to represent quantum states. So those are options. The big issue here is getting results which are stable, results that can be validated somehow, because the validation of approximations are not usually easy to do, in particular if you have a huge systems. But those are techniques that people are using today to go beyond the limitations, the memory limitations that I mentioned before. So if I ask you, is that sufficient, is that enough? Well, unfortunately, the answer is no. So even if you do approximations, even if you go for those Monte Carlo techniques, tensor network techniques, and neural networks, we can do something. So we can represent a subset of the overall possibilities in terms of quantum states, but that's not enough. So we should really think seriously about algorithms for simulation, but also implementation of hardware that could allow us to test those algorithms and cover this diagram by looking at more broad distribution of quantum states. Yeah. Finally, is quantum computing reasonable? Well, there are many things that we can do. Depends on the problem. There are some applications. There are some intrinsic applications that are clearly more advantageous to be done on quantum computing, on using quantum bits, because we are in the Hilbert space, so we have access to more flexibility, other algorithms that will scale in a different way in comparison to the classical counterpart. But obviously, there are many, many other things that we have to consider. For example, we could, this is an example that is very famous. We can take variational quantum circuits and generate a variational quantum computer. So as I presented before, we have the unitary, a parametric unitary u theta. So what we can do is that we can take this parametric unitary theta and try to figure out what is the best set of parameters that approximates our law, our optimal operator. No? And I will show you now in the next slides. For example, there are theorems like the Solovay-Kita-F theorem that give us some hints about the sizes of the circuit and the feasibility of implementation. For example, let's consider this problem. Suppose that I am in the Hilbert space in the yellow initial condition, and my goal is to move from the yellow to the green. This is the optimal pattern that is represented by the alpha set of parameters. I can try to build an operator by just multiplying or by creating a series of unitary gates for a different number of qubits. Now the question is, if I manage to write something like that and create a parametric gate that I can fine-tune, well, I should try to go and to optimize and get very close to the optimal solution. So this is the typical layout for a variational quantum computer. Now the Solovay-Kita-F theorem, what it does is that it supposes that there is an optimal solution V that starts from the initial state and goes to the final state, and my approximation U alpha that will bring us close to the optimal solution. And if we compute the distance between my approximation, that here is represented by the product of a dense set of unitaries minus the target solution, if this is my approximation with an error delta, the theorem tells us that the approximation will scale with order logarithm of C of delta minus 1, where C is smaller than 4. So what this theorem is telling us is that the approximation is feasible in the sense that I can write a finite number of gates due to the fact that the scaling is logarithmic and the power is lower. So it's lower than 4, no? So it's very bounded. So at the end of the day, if I'm looking to optimize solutions, then with this approach, the variation approach, I could do something reasonably well. Now, so I can start thinking about variational encoders, eigensolvers, machine learning. So I can really try to put down some algorithm that will take a benefit from this representation and the tolerances that are represented by the Solovay-Kita-F theorem.
The theorem is independent on the set of universal gates that you choose, right?
In this case, yeah, it should be dense set, no? Usually dense set of gates. That's the way to go. The problem is that unfortunately we are bound by those gates that I showed before. No, we are not using pulses, for example. If you use microwave pulses, then you could have whatever. You could try to define all the possible operators. But in this game, usually use
so this theorem applies for the set of gates?
dense, yes, the dense ones, yes. Right, so this, for example, is an application that could be carry on if you are interested in building optimal solutions. Okay, so this is just a quick introduction to what is a qubit, why you need to simulate, what are the operators, what are the challenges in terms of simulation sizes and all that. Now it's time to have a look at this representation, in particular software representation. And I will try to explain a little bit why we are talking about Qibo and what is Qibo. So in our case, quantum computing can be viewed as a set of two independent challenges. So one is simulation. So how can I simulate the system and design algorithms? The design of algorithms is quite important because is the origin of the potential applications that I can do, like post-quantum cryptography, search problems, simulation of quantum systems, quantum annealing, machine learning, and beyond. So simulation is crucial in order to do that. On the other branch, the other challenge is hardware. So how can I design the quantum chip, the quantum process unit, the QPU? How to design, how to fabricate those devices, how to control, characterize, and calibrate. Now, those are always questions that are important from the experimental side, but also are connected to the algorithms, or the family of algorithms that I'm planning to run. And the glue, so the glue that brings this set of applications together with hardware is software. So the software is extremely important. Now, in our setup, and in general, in many applications that you face even today and in the next days, we have a problem that you want to solve. We go directly to the code and you write a high-level description of our algorithm using physics, usually. And then the first goal is to simulate. So we take our classical computers and try to simulate the quantum system by using CPU, eventually GPUs or multi-GPUs, depending on the infrastructure that we have available. So the fast classical simulation of quantum systems is mandatory to do. As soon as we are, let's say, happy with the results, or we see some, good chance of getting something interesting, we go to the second branch. So we try to deploy our high-level representation algorithm into quantum hardware. So the quantum hardware will require optimization because there are different quantum technologies, as I mentioned before, superconducting, ion traps, and so on. We have to deal with calibration and the fact that the system fluctuates. There is a natural drift, so of calibrations over time. So my algorithm might have an impact. So I can monitor that over time. And finally, all problems related to errors. So noise, in particular, I can try to do error correction. I can try to do error mitigation. I have to think about the best way to suppress uncertainties, not the statistical ones only, but also the systematic ones. Those are the two most challenging parts of my problem. Now, you see this diagram. The diagram is very clear. Problem, solution in terms of code, and then deployment. So ideally, I don't want to specialize my code for each specific task. And therefore, if you have to carry on or have to design a lab, this lab will have to provide a set of tools for model and applications design. As a second point, simulation software. As a third point, hardware control drivers for commercial vendors, for open source firmware, for whatever you have in front of you or you are able to buy or fabricate. Calibration routines and monitoring tools, and access. Now, access is also important because if there are many people using the system, or if you wanted to deploy different algorithms, this is important. So the problem is an interdisciplinary set of modules, and ideally you'd like to see all those modules open source because we are working in an academic environment, and as we know, also for commercial environments, open source is usually pretty good because you can grow, we can have a feedback from all the people. So in principle, those are the most important ideas when carrying on a project in a lab. Now, what we try to do is that given that we are involved in multiple research institutions, we try to have a look at the software available, and we realized that unfortunately all those points were not available in 2020, and we had to implement ourselves. So what we did is that we defined Qibo, which is our library, our framework. Is a sort of a hybrid quantum operating system for self-hosted quantum computers. So self-hosted means, yes, I have a lab, I fabricated my chip, I can put my chip in operation, and then I need software to operate it. And this Qibo ecosystem, it provides tools for the lab and a language, so a programming language in the sense of an access programming API, so where I can have my representation of qubits, gates, and write algorithms. The idea was to do something that was fully open source with modular design for simulation, hardware control, and control electronics, plus all the features that are usually common nowadays with programming open source. No? So here you can see the current landscape in terms of macrostructure. So Qibo provides a language API for quantum annealing, quantum computing, and quantum information. Those implementations can be deployed on simulation backends. We'll go later about this, but we can simulate using different technologies. Afterwards, you can deploy the algorithm on cloud backends, or if you have a lab, using the hardware backend. So the hardware backend is connected in a special set of tools for drivers, for transpilation process, and based on this setup, you can create also applications that are involving from machine learning to quantum chemistry to any other application that is using and relying the different modules. You can install all, we have it divided into colors because each color represents a module. So if you just need a language, you can download only the purple package, which is Qibo, and operate here. But then if you need specialized simulation backends, you can install specialized libraries like a QiboJIT. If you have a lab, you can go for the Qibo lab installation. So this is our modular infrastructure, and it's being developed in this ecosystem that you see here. So here you have all the countries that are contributing to Qibo, all the different institutions, and those institutions with this icon here, the chip icon, this representation means that we have a quantum hardware available. For example, you have it here in Spain, you have in Italy, you have in UAE, you have in Singapore, in Asia. So we are trying to create a common set of tools that are used by academic institutions and that are standardized somehow. So you have the same basic infrastructure and language. Now, just a brief set of slides about simulation. So, as I mentioned before, simulation can be done using multiple technologies. For example, exact CAT simulation can be done with NumPy on CPU. You can also do it with just-in-time compilation on GPUs. We can also use machine learning tools like TensorFlow or PyTorch. So, but for me, today I wanted to show QiboJIT, which is one of the fastest approaches that we have. So the QiboJIT is just-in-time compilation of exact simulation CATs. What we do is that we take the tensor dot operator that I presented in the previous slides, and we go through this diagram. So if the code has to run on CPU, we design custom operators using Numba, which is a just-in-time compiler, uses LLVM in Python to compile our operations, or NumPy tensors if you want to deploy the system on a system with few qubits. So the CPU approach is performing in-place updates of the state. So the state is allocated only at the beginning, and then all its components are replaced during the tensor dot operation. So there are we don't copy this state into the final state. So this is important because otherwise we don't have memory. And the second thing is that we specialize operators to the unitaries that we apply. So if you know that a unitary is symmetric or there are some specific structure, we reduce the total amount of operations to match the best performance possible. This is done also to the left of the GPUs. So we can have the QPy tensor representation and the custom operators using CUDA that are also compiled just in time. So this is the explanation of why we call just-in-time compilation. Now, in terms of performance, for example, what you should expect is that Qibo JIT, if in this plot I'm showing the simulation time in the y-axis and the number of qubits in the x-axis. So all the curves, they are representing Qibo JIT performance numbers on multiple hardwares, from GPUs, the NVIDIA GPUs are those in blue, or AMD GPU in green, to CPUs. So you have the AMD EPYC 7742 and the Atos Quantum, the QLM system. So you can see here that the orange curve, which corresponds to this Atos machine with 6 terabytes of memory, is the only one which reaches 37 qubits because it has 6 terabytes of memory. So that's why you can go up to this point here. But in comparison to the red curve, that is the AMD EPYC, the speed is not so good. So you can do a little bit better because the clock of the AMD CPU is slightly faster than the one available in the Atos system. However, on the other hand, you can see that the AMD is bound by 2 terabytes, so you cannot go beyond 36 qubits. 35 qubits in double precision. Now, if I move to GPUs, for example, if I take the NVIDIA RTX A6000, I can do much better in terms of time, so there is a huge gap in orders of magnitude in performance, but I am memory bound, so I cannot go beyond the 32 qubits. GPUs are increasing the size in memory, but still not, they're not super fast nowadays. So the only solution for us is, for example, to split the computation and do multi-GPU configurations, like these points that you see here, where we use one or more GPUs to distribute the state computation. This is possible to do, but there is a lot of memory and crosstalk between the devices. So there is a clear deterioration in performance. And as you can see here, we have an improvement in time in comparison to the CPU, but the asymptotic behavior is similar to the one from the CPU. So this is the possibilities that we have using state vector, but still interesting because if you have a memory, you can go up to important numbers. Now 37 qubits is a lot already to simulate and play with. And by the way, you get exact results, so there is no approximation involved on that. If you compare Qibo JIT to other libraries, I mean famous libraries like the ones from IBM, like Qiskit, Intel with Hybrid Q, the QC GPU, or even if you go to Qulax and Project Q, in this plot you can see for 30 qubits in a single precision for this first row and in the second row double precision, you can see that for multiple circuits, for the quantum Fourier transform, the variational circuit, the supremacy circuit, the quantum volume, and the Bernstein-Vazirani circuits, the performance on CPU of Qibo, so the blue bars, is pretty much similar to the other libraries, or in some cases even faster. But the nice feature is if you look at the dark blue, which corresponds to the Qibo on GPU, our predictions are usually very, very fast, very efficient, even in comparison to those libraries that are dedicated to GPU, like the QC GPU or even Qiskit with a GPU. So this is important to remember because obviously over time code software improves, but given that the community doesn't have a standard, if you try to do a benchmark and you see those results, then there is a lot of work to be done. And there is some discussion why this is happening. So why exactly Qiskit is doing, why we get a better result. So there are many things to be accessed. No? And again, that's why we had to design a proper framework in order to clean up and try to understand all the different pieces and components of the code. Okay, now just a few comments, few slides about the lab tools. So when deploying the circuit into a hardware, a chip, we have to start from the circuit definition and then a transpilation process. So the transpilation will take my circuit and try to understand if the circuit can be deployed on hardware. Why? Because the hardware might have a topology which is not exactly matching what I have to do. I might have an architecture which is based on a cross, for example. So it's quite possible to find a qubit chip where I have this kind of connections between qubits. So if I plan to do control knot between this qubit and this other one here, so if I wanted to connect those two, I will have a lot of troubles because there is no direct connection originally from both objects. So what I have to do is that I have to first of all swap one qubit. For example, I have to take this one here and bring it to the center and then create the control knot between my original qubit and the qubit at the center. No? So those operations are done by the transpiler, trying to understand the architecture and then moving the gates in the right way.
The state.
Yeah, the state. Yeah. So this is what we do here. After achieving the circuit transpilation, we go one step further with the hardware deployment. So we select our electronics and we ask the electronics to execute the code directly on chip. And finally, we collect measures. So this is the standard process. Now, what we did is that we have designed the Qibo Lab module. That is, I mean, you can, if you want, you can download, you can have a look. I mean, we are not touching this in this course, but just to give you an idea, the lab module defines microwave pulses, so the pulse representation that we send to the device, the transpiler, and drivers for multiple set of instruments, from commercial products to open firmware products, such as the radio frequency FPGA. So all that is automatically done, so you can just prepare your algorithm, and then the translation process and the communication to the hardware will be automatically performed by the Qibo Lab module. And you can design your own platform, you can define all the parameters of your electronics, you can calibrate, so there is plenty of possibilities when manipulating Qibo Lab. A specific opportunity is the one that we have to calibrate. So if you take Qibo Lab, then we can go ahead and calibrate single qubit gates or 2 qubit gates. And when calibrating, there are many routines that have to be executed in order to extract the T1, T2s, so the relaxation times, in order to understand what are the frequencies and the amplitudes of our pulses. And these operations can be done directly using the Qibo Lab module. Exactly. So here, just another plot with the performance. So in the y-axis, there are some algorithms like resonator spectroscopy, qubit spectroscopy, Rabi, Ramsey, T1, T2 experiments to their determination, single-shot classification, and standard RB. In the x-axis, the experiment duration. And the thing that you have to look at this plot is the black curve. So the black bar corresponds to the theoretical execution time that you have to wait. That means this is the minimum amount of time that you have to wait in order to measure one of those observables. Now, if you compare this theoretical time to electronics, so commercial vendors or open source, open firmware vendors, you can see how much they deteriorate the theoretical time. So there are some observables, like for example the Rabi amplitude, where all the vendors' performance and the theoretical time are very close to each other. But there are other applications like the standard RB or the single-shot classification where there are huge discrepancies between one instrument and another. So this is another point that is important, because when designing a lab and operating a chip, you have to decide how to do it. So this might have an impact on the performance of your algorithm. So you have to be careful when deciding and how to tune. With Qibo Lab, you can do that. So you can really deploy and check and then decide what to do and how to improve the communication. Okay, now just to complete, if you take all that together, then you can have applications in real life. For example, in this plot, I'm showing some randomized benchmarking that was done using Qibo, Qibo Lab, and QuiboCal. So we can really go ahead and randomize the circuit evaluation and then measure the survival probability for multiple lengths of sequences. So in practice, we are just creating circuits with different sizes and then computing the survival time. So how long we can preserve the fidelity representation of our gates. While on the right side, you can see the Bell's inequality test. So the system is represented by the bear curve. If the bear curve is larger than the classical bound in blue, you are violating. So you know that we are dealing with quantum with a quantum state. And in this case, there is a violation. And in fact, if you apply to the violation the mitigation uncertainty, the mitigation strategy, then you can go up and the violation is even larger. No? So this is a typical examples of applications if you are in a lab testing the device and trying to understand if your system is calibrated. Another one is regression. So if I take Qibo, the Qibo calibration module and Qibo lab, I can try to do variational quantum computing. For example, here in this plot, I'm showing a target function in black, which is just a function in X. And I can define a quantum circuit that will try to mimic the behavior of this target black function. And this is the experimental result. So you can do that, and then at the end you achieve a regression fit. So this is a fit obtained from the quantum computing. And the total amount of time that you have to wait in order to obtain this distribution is less than 1 hour of fit. So you can really go down step by step. So you can compute the gradient, and then at each step measure the loss function and extract the best set of parameters. So those are things that you can do nowadays without any particular issue. Yeah. So as an outlook, today what we will do now after the break is just go through the software, try to build some quantum circuits, try to represent all the gates, the measures, and have a look at what we can do in terms of simulation. We are also talking about ancillary qubits, Grover search algorithms, and noise, and how to mitigate noise. So this is the next that we will do. If you have questions, if you want to have more details about the library, you are invited to just visit directly the documentation online. And obviously, if you have questions, I mean, you can just ask us. We are here, so we are trying to cover the basic aspects. But if you have interest and if you have some specific feature requests, you can just go directly to the land page and then try to look at the documentation or even ask us directly from there. Yeah. So with that, we think we're ready for Let's Code. No. And if you have questions, please let me know. Otherwise, we make a break and then we try to start our discussion.
Questions? Somebody wants to ask something? Okay, probably not. So we will go directly to the code part after, let's say, 15 minutes. So in the code part, who will start? You will start, okay? So we will do some exercise and we will get some practice about this library and more generally about quantum computing, right? So, by the way, if you have questions, please ask questions also during the talks such that we can make more interactive the session and make more funny, hopefully. So see you all in 15 minutes, more or less.